You can hear me? Okay. Okay. We were talking about composites, and I just wanted to wrap up a little bit on composites. I talked about composites. We use huge numbers of huge amounts of structural composites, concrete for buildings, asphalt for roads. But most of the work done on composites we talked about is done on aerospace composites, because there's certain things that just can't be built without the lightweight and the advantages of aerospace composites. And I put up the V-22 Osprey before. That aircraft could never have flown if it weren't for high performance composites, which is not, concrete and asphalt are not exactly high performance composites. Although there are still people who do research, actually there's quite a bit of research now over in civil engineering on improved concrete, because there's so much concrete used and it's so inexpensive, and they'd like to make it better, particularly in tensile strength. There's a lot of work done on asphalts, particularly in colder climates, because the asphalt expands and contracts, and you have to, in Alaska, you get much above Fairbanks, and they don't even bother to pave the roads, because you'd have to rebuild the road every spring. The winters are so severe, it would contract and crack and whatnot. But they still do a lot of research. I was at the University of Alaska in Fairbanks 10 or 15 years ago, and they had a big program for the southern half of Alaska to get better asphalts, because they spend a tremendous amount of money repairing those roads, not because of a deficiency in the material, but there just is no material that survives the severe winters, and that's why you can watch ice road truckers, right? I mean, you go north of a certain level and they just use ice for the road, right? Anyway, composites are fundamentally the marriage of several materials to get what the composites people tell you, the benefits of both. Now, the other side of that is to get the detriments of both, okay, which they don't usually talk to you about. So back 30, 40 years ago, 35 years ago, someone up in Canada developed a technique to mix silicon carbide in with aluminum and cast it. And so you had a very inexpensive way of making aluminum silicon carbide composites. I can't remember the name of the company, but it's the late 70s, early 80s. And they were getting press all over the place. Okay, there were lots of interest in their material because they were good public relations people. And so I sort of modeled this particular graph on that material. In fact, this graph comes out of probably the mid 80s. But the problem is, this is sort of looking at the metal specifically. In this case, I'm thinking of aluminum. And for any material, if you're going to select it, there's not just one parameter, there's a number of parameters that might be important. And depending on the application, those parameters vary, okay? Strength is always an important property in structural materials. We've talked about toughness, it's an important property. Aluminum is just not a very strong material compared to a lot of other things like the ceramics or steels or whatever. So aluminum, it would be great to improve its strength. Aluminum has excellent formability, excellent jointability. If it's not too highly alloyed, it's got very good corrosion resistance. It's actually pretty good corrosion resistance in general. And it's reasonably affordable. So, and it's lightweight, of course, so far as that goes. So this is sort of and the circle here is supposed to represent how much of a property you need, okay? And if you're beyond the circle, you've got enough of the property, but aluminum just doesn't have enough strength for many applications. And so people thought, well, you just marry that with a ceramic. Here's my ceramic, okay? And a ceramic has tremendous strength, and ceramics, you know, bricks, mortar, lots of aluminum oxide is a ceramic, have reasonable affordability. They're not terrible, and the ceramists like to tell you that they have fantastic corrosion resistance, and in many applications they do. Certainly atmospheric or aqueous corrosion, ceramics are excellent. They got lousy formability. You ever try to, whack a piece of ceramic with a hammer, you end up with lots of pieces of ceramic. Okay? If you look at jointability, it's a problem. Toughness is a problem, but you could marry it with the metal, which has deficient strength, and hopefully you'll get an improved product that has the advantages of both. But in fact, if you look at what you get with the composite, these aluminum silicon carbide composites, for example, yeah, you can get the strength you need as you add the hard silicon carbide particles to the aluminum, but your toughness is lousy, your formability is lousy, your jointability is lousy, your corrosion resistance is lousy, and it turns out your affordability bites the dust. And in fact, if you put everything together on one plot, it kind of looks like this for all of them. You started out with one material with high strength, one material with low strength. You marry the two and you get a composite between that is beyond what I need for strength. It's beyond the circle, but I lose everything in these other areas. Okay, so the point is, composites can be used as a marriage of materials to get the advantages you must have, but you're going to pay a price, and the two prices are going to be cost price, but there's also property price. Virtually every ceramic, every composite has paid a big price in recyclability, formability, sometimes corrosion resistance. Composites have very specialized niche applications. And in fact, if you think of concrete and asphalt, they have the largest application in huge volumes, but they're still sort of niche. I mean, what else do you build out of asphalt other than roads? Okay, and concrete can be used in a lot of things, and it's fairly inventive. And actually, if you've seen artisans in concrete, I mean, there are some people who do buildings that look like fancy stonework, and it's fantastic. I've always been surprised they didn't do more of that, but anyway. But the point is, composites enhance a few of the properties while degrading other properties, and you've got to be aware of that. You can't just buy one thing. Yeah. Yeah. Yep. Yep. Essentially, you give concrete zero strength in tension. It actually has 2 or 3 KSI strength in tension, but in compression, it's got like 60 KSI strength. Okay, so if you're talking about loading a beam, okay, here's a beam that's flexible. If you're talking about loading a beam, then yeah, the bottom's in tension, but the top's in compression. Concrete's great there. But basically on the bottom, when they calculate the strength of that concrete beam, they treat it only steel on the bottom. I mean, it's the cross-sectional area of that rebar. And the rebar doesn't have to be welded. You can overlap it and you just use, and remember the rebar, I still have it. Here's the rebar. You can pass it around, it's galvanized rebar. But it's got they rolled on these notches to give it so it can interlock into the concrete. But you can overlap it, and as long as you have enough overlap, it's as if it was joined, okay, in terms of the tensile strength, okay? Does that answer your question? Okay, but yes, in the design, they give it zero strength in tension, but that's a little unfair, okay? Other questions? Okay, composites, people will talk about composites being inexpensive. Don't believe it. Composites inherently require more processing steps. That was one of the reasons the aluminum silicon carbide was so exciting. You could make it with a casting technology, so it wasn't going to be much more expensive. But most of the time, you have to make material A, you have to make material B, and then you have to join them together. Now, there are some intermediate composites that have been used widely. The one I'm thinking of, rather than asking you, playing the quiz game, is fiberglass. Okay? Been using it for 60, 70 years. Ever since plastics really started to become popular in the 1950s, after World War II, plastics started coming into their own. And people found, oh, you can take glass, which can be extremely strong. Okay, people don't realize how strong glass fibers can be. Most lay people don't, but glass can be. Freshly made glass, in terms of strength, not toughness, is stronger than steel. Okay, it's just like piano wire. It's super strong. And if you coat the surface so it doesn't get attacked by the moisture in the air, then the glass will retain much of its strength. And if you have lots of fibers, you have the redundancy, and you can get a very good structure. When I talk about glass being strong when it's freshly made, glass has no imperfections on the surface, okay, if it's made properly. And it's the imperfections on the surface of a brittle material that weaken it. And so I can't do it. My old thesis advisor used to teach 3091, and he tells me that he used to live up on he still lives up on the North Shore, but they had a Sylvania light bulb plant up there in Danvers, and he used to stop in the morning before his lecture and get freshly made light bulbs. Okay, they're just fresh blown glass, and he'd bring them in, and for his 10 o'clock lecture he could throw them across the room and they would bounce because they were freshly made. The glass had not been attacked by the humidity in the air. After a few days, you throw it across the room and it'll shatter just like any light bulb you know of, okay? But freshly made glass, before it starts to get etched by the moisture in the air, it actually does on a microscopic scale, but it's so brittle, these submicron imperfections destroy its strength, okay? But fiberglass, people making fiberglass realize you can have tremendous strength, and you marry a protective adhesive coating, basically the plastic, with the fiberglass, and you end up making boats that don't corrode, which is an advantage. What else? What automobiles? What were the first fiberglass automobiles? The Vet, the Corvette. Anybody can make a fiberglass $50,000 car. You can't make a $20,000 car out of fiberglass. Although in the 1990s we tried to start making truck beds out of plastics, or plastic resin molded composites and stuff. And it turns out people love them. Joel Clark was working with, I think it was Ford, and they made some of these truck beds for pickup trucks, and they gave them to a mine site to try to, get a lot of wear on them. And they gave some steel truck beds and some fiberglass truck beds, and they were supposed to put them in service for 6 months and send them back so they could evaluate them at the research center to see how they did. The companies, the coal companies, didn't want to give back the resin molded composite beds of the trucks because they didn't dent, they didn't crack, they were resilient. There's the steel dented and you couldn't close the tailgate and all this other stuff, if you're dumping things into a pickup truck and abusing it like they do in a coal mine. And so it turns out the not fiberglass, but the resin molded composite truck beds, and now what they do is they give you liners. Okay, it's still steel on the outside. And the reason for that is the plastic is still just more expensive. Okay, this is something I put together years ago. But for high volume structural materials, I'll have to make some of these again, where both cost and fracture resistance, we quickly find that for constant volume, okay, the approximate cost per pound, actually this cost per pound in dollars. Steel back then was about 20 cents, about 40 cents now. Aluminum is $1.20. Simple composites like this truck bed were $2 to $10 a pound. Now you get 5 times the volume with that composite, so it's down to 40 cents to $2 on a volume basis, but it's still more expensive. And just simple plastics, not composite plastics, are still more. Everything's more expensive. Even wood is more expensive than steel. Aluminum has a 2.5-fold advantage in density, and so doing this on a cost per pound is not necessarily the fairest way to do it. You can figure it out, and there's all kinds of metrics you can use and stuff to figure out what is best. That's about all I'm going to say about composites right now. I may talk about it a little bit more later. Does anybody have any questions on composites? or anything else. Okay. So I want to talk now. I'm going to get into specific materials and what their advantages and disadvantages are. And what's the first material I'm going to talk about? Steel. Okay. Okay. Actually, composites was sort of the first material I talked about, but steel, because it's used in such high volumes. It's made everywhere. Okay. There are hundreds, literally hundreds of very large steel companies around the world, and I told you whole countries will invest in building their steel mill because the big integrated steel mills are too expensive for a single company to build in the last 40 years. What people don't realize, and if I compare that to, let's take aluminum, the second most widely used metal, and on a weight basis, there's 40 times less aluminum made than steel. Aluminum's a little over 2% of all metals, steel's over 90%. So on a weight basis, aluminum's 40 times less. On a volume basis, it's 20 or 15 or 20 times less in volume of material that we make. Aluminum's been around technologically almost as long as steel, but in fact, it's because steel has this unique combination of strength, toughness, and cost that we've gone over ad infinitum here. But you need to understand that there are hundreds of steel companies. How many aluminum companies can you think of? Well, you can think of one, Alcoa, right? But there are other aluminum companies. You've heard of Kaiser Aluminum, maybe? No, you haven't. If you're from the West Coast, you would have heard of Kaiser Aluminum. You've heard of Reynolds Aluminum, right? You might know how Reynolds Aluminum got started. It's the same Reynolds as Reynolds Tobacco, and they needed something to wrap their tobacco in, and so they started making aluminum foil around 1900. And they kind of grew the aluminum business separate of the tobacco, but it's the same R.J. Reynolds Tobacco Company, or R.J. Reynolds family out of Richmond. And that's the headquarters of Reynolds. There's Alcan, Aluminum Company of Canada, which is actually a spin-off. Trustbusters broke up Alcoa. Alcoa and Boeing, I told you, Alcoa, Boeing, and Pratt & Whitney were all once together, and at some point they broke them up, and then they also broke off the Aluminum Company of Canada. Alcoa just had a monopoly. But there was Charles Martin Hall, who kind of was the founder of Alcoa, but there was Paul Héroult in France, who had also discovered the same thing and just got to the patent office a little bit too late, and Hall beat him. But his company was Péchiney in France. And Péchiney was just bought by somebody else. But anyway, I can't remember. But anyway, you can't even name very many aluminum companies. I can't name more than a dozen. And I've been in this business for years, longer than you've been alive. So, but I could go off and rattle off the names of dozens of steel companies, although to a certain extent they've been consolidating into some huge conglomerates, mostly because their profitability was so bad. And why was their profitability bad for the last 30 years? Because their productivity was so good, okay? They had improved their productivity so dramatically that they almost drove themselves out of business competing with each other because of their increased productivity, okay? And so Wall Street, those people over at that side of campus can't figure these things out, that was not a good, that they were not an ancient material that was no longer useful. They thought they were just an unprofitable, backward industry. Well, they were, maybe some of their management was backward, but it's still an important material. And there was this guy, Mittal in India, who just started buying up steel companies for a song. And now ArcelorMittal is probably the second largest steel company in the world, and he's making billions, okay? Actually starting to lose some billions right now, but anyway. So, what is the most technologically advanced material you can think of? Most people would think silicon, right? We know a lot about silicon, right? It's fundamental to semiconductors. What's the size of the silicon industry that makes computer chips? You know, the Intels of the world, or the advanced micro devices out of Boise, Idaho. Anybody have an idea of how big that industry is? tens of billions. Well, actually, Intel's about 30 billion last I looked. Okay, it turns out about 200 billion. Intel is a significant fraction of all the world's semiconductors, and I'm talking about the chips. I'm not just talking about the silicon. Silicon foundry business to grow single crystal silicon, that might be $10 billion or something. But the actual chips, when they add all that functionality to the little lump of silicon, single crystal silicon, it's a couple hundred billion. Whereas the steel industry tends to be about $1 trillion industry worldwide. And the aluminum industry tends to be about a $100 to $200 billion industry. So the aluminum industry and the silicon industry are similar in size. And we often think, oh, you know, if you go and look at the course offerings at MIT, you would think that silicon is the wonderful wonder material. This is the silicon age. And it is a wonder material in many ways, but in fact, the most technologically advanced material in terms of how much we know scientifically about it is steel. Okay, and I've only said that to a few people a few times. I haven't. Well, I've had some faculty challenge me on that, and then I start pointing out some things. But we know a tremendous amount just because of the size of the industry. There are people, all kinds of people around the world doing research on it because of its economic importance. Now, it turns out it has not seen tremendous growth in properties. Whereas, boy, you look at silicon, you can say, well, the number of, transistors on a chip is, doubling every 2 years according to Moore's law and stuff. And that's true, and the performance of the semiconductor is much greater. And people say, oh, but silicon, it may only be $200 billion to sell the chips, but it goes into all kinds of products that are worth a lot more than that. And I said, yeah, but did you know steel goes into products like buildings and bridges in automobiles that are worth a lot more? About 25% of the world's GDP relates to structural materials. Okay? Bridges, buildings, aircraft, and steel is a large fraction of that. Why does steel have some of these advantages? Strength, toughness, cost, but there's other things. The ability to form it. It's actually very easy to form steel. You can stamp out sheet. You can bend big heavy sections. You can join it easily. One of the advantages that it has, Christine's thing about she wants to do swords, is you can form it when it's soft, and you can transform it to being hard. And that's also an advantage with aluminum. Both steel and aluminum, their inherent strength, steel's about 35 KSI basic strength, and you can harden it to almost 10 times that in certain conditions. Aluminum is about 8 KSI, and you can do even better than 10 times. You can get about 12 times the strength. And so actually your homework problem for Monday is to think about what is the highest strength application for aluminum alloys. And I'll bet none of you get it. You're going to guess aircraft and it's, or spacecraft, and it's not. Okay, but anyway, I don't know if you can even find it. You can find it on the web, but you'd have to know where to look. Okay, but I asked you for a homework problem, and I think Dr. Belmar gave it away, and he tells me I gave it away earlier this semester. What is the Achilles heel of steel? Corrosion, rust. Yes. Okay. Why do they galvanize that rebar? Why are they, when you're driving around New England in the summer, why are they always tearing up the bridges on the highways? Because the rebar in the concrete rusted, the rust expands, causes the concrete to spall, and you end up with potholes on your highways. If someone hits them at 70 miles an hour, they'll have a wreck, and so they have to go in about every 20 years and rebuild the bridge deck to replace the rebar. People have tried making stainless steel rebar, plastic coating the rebar, going to stainless steel rebar. They've even gone to nickel-based rebar, which you couldn't afford to build all the bridges. There's not enough nickel in the world to do that. But nonetheless, people have tried all kinds of things to fight that form of corrosion. The corrosion scientists estimate that in the United States, we lose about $200 billion a year in corrosion, the cost of corrosion. And guess what? probably 80–90% of that is steel, because 90% of all the metal made is steel. Okay, so the Achilles heel is corrosion, and I did have something talks about the 8 forms of corrosion, and I have a handout for you. Comes out of the 8 forms of corrosion. There are actually 2 different 8 forms of corrosion. One comes out of a book that's in its 3rd edition, Fontana and Green, which is Ohio State has a big corrosion research center going all the way back to the 1930s. Professor Latanison, who used to be here, is Professor Ballinger's thesis advisor, came out of Penn State and Ohio State studying corrosion, and Fontana and Green have their index to the book talk about the 8 forms of corrosion. Except their 8 forms are different than this 8 forms. This 8 forms, good thing I handed out something. This is mechanics of attack. Okay, and the 8 forms that Fontana and Green break corrosion into are sort of the chemistry of attack. Okay, so they're a little different, but there's something called uniform attack. In the area of steel, we call that rust. Okay, so as far as that goes, we have localized attack, which can be pitting or it can be gouges. We have crevice corrosion, we have erosion, cavitation, where you have bubbles collapse and create pressures that break off the protective surface oxide. One of the problems, most steel does not have a protective surface oxide. Now, there's a lot of steel that does. Here's a piece of steel, black iron pipe. If you go down the basement of most buildings or a boiler room or something, you'll see this stuff. It's unpainted. Okay, so black iron pipe, when it's hot coming off the rolling mill, will form at high temperatures Fe3O4, which is called magnetite. Which is a magnetic form of iron, and rust, which forms at lower temperatures in the air with the moisture around, is Fe2O3 dot a bunch of H2Os, and that's hematite. And there's also wustite at higher temperatures. But it turns out magnetite has a volume ratio and coefficient of thermal expansion that is such that when it forms on steel, it forms and has a coefficient of thermal expansion that it will adhere. Rust, on the other hand, when it forms, can have a 4 to 10 time volume change, depending on how many H2Os are in it and how much chlorine might be around and whatnot, and it will flake off. And so we've all seen rust, okay, flaking off. Typical atmospheric corrosion rate of steel is about 0.004 of an inch per year. So 40 years, you lose 1/8 of an inch, okay, or so, from both surfaces. So if it's a big heavy steel beam, you know, why are they going to rebuild the Longfellow Bridge? It's rusty, okay? But it's been there for 100 years. But they started out with big heavy sections, and even if it lost 1/8 of an inch in 40 years, the growth usually goes as the square root of time. So in 80 years, it only loses a 1/4 of an inch. But after 80 years or 100 years or whatever, the Longfellow Bridge has gotten rusty in enough spots. I mean, if you've driven by it or walked across it or whatever, the handrails where the snow sits, and let's face it, snow in New England is acid rain. It's just frozen acid rain. And when it melts, it's a pH 5.5, and it will start eating away that steel. And you see the fence rails, the guard rails to keep you from falling into the Charles, are all rusted away all the way through, perforated after 100 years. Okay. Now, some of them is cast iron, and cast iron forms it's got a lot of silicon in it. It forms a glassy silicon layer, so it's a lot better. Or corrodes less. Cast iron corrodes less. But there are these 8 forms of corrosion, and actually, I do a a short corrosion course for the Navy folks, but of about 6 or 7 lectures. Anyway, so you can talk about 8 forms of corrosion. One form, not all forms occur to steel, but one form that does occur is stress corrosion cracking. Okay, steel will form cracks in certain environments, even if it doesn't rust. It can crack in other environments. Stress corrosion cracking is most common with the stainless steels, and we'll talk about that maybe on Monday. But the form of stress corrosion cracking that's most harmful to the steels is hydrogen embrittlement. And Dr. Belmar talked about that, but hydrogen embrittlement, the steel has been around, is exposed to the atmosphere, and hydrogen, it reacts, and the oxygen forms Fe2O3, releasing hydrogen when it reacts with the water. And if the hydrogen diffuses into the steel under certain conditions, or if it's there from the steel manufacturing, and you put it under tension, it will call what we call delayed cracking. Basically, they call it a static fatigue test. Just take a bar of steel that's got hydrogen in it, or you can charge it with hydrogen while it's under tension. You put it under tension, and if it's got hydrogen in it, and you're at more than maybe 40% of the yield strength in tension, the hydrogen will diffuse to little imperfections like inclusions in the steel, and the hydrogen likes to go to the larger crystal lattice, which is the part that's in tension. If you have an imperfection around an inclusion, and the inclusion is in tension, then you will essentially, if you think of your volumetric strain field, there's more space here on the sides, and the hydrogen will go there. It will weaken the steel, and you just hold it under constant stress, not fatigue. Just hold it under constant stress, and in somewhere between 48 and 72 hours, it will crack. It will separate. Okay, so they're welding nuclear submarines down in Groton, Connecticut, and if they don't control the hydrogen while they're welding, and these big egg crate type of constructions to make a high strength pressure vessel, guys will be welding during the day, and the guys at night who are welding will hear a bang like a rifle shot in the shop. And that's a brittle crack that just ran through the steel and broke it right in two, okay, due to hydrogen embrittlement. Also called delayed cracking. Now, it doesn't usually occur, it doesn't occur usually within the first 1 to 4 hours. If you look at ASTM specs, if you do something like electroplate steel that could introduce hydrogen, the ASTM specs say you must put it in an oven at 375 degrees Fahrenheit. So this is like cooking a cake. It's not terribly hot. And that will diffuse the steel out, the hydrogen out of the steel, before it has a chance to accumulate at the imperfections and cause cracks. People have taken polished sections of steel and put them in a microscope in a aqueous solution, and they actually can look in the microscope and see bubbles of hydrogen forming, okay, right there at those crack tips, okay, over time. The hydrogen accumulates at the tensile stress region because there's more space, and if enough hydrogen gets there, you get hydrogen embrittlement, and the steel will crack. Dr. Belmar sent around a piece of bolt that had cracked in service, and then he and I are still debating about whether it was hydrogen embrittlement or stress corrosion cracking. The difference between hydrogen embrittlement and stress corrosion cracking is 70% of the time metallurgists make no distinction. But in fact, one occurs at the anode and one occurs at the cathode. And yesterday you learned about anodes and cathodes and corrosion. Hydrogen embrittlement occurs at the cathode. Oxidation corrosion occurs at the anode. And you can very simply change the polarity, and you'll either be cathodically protected and you could get stress corrosion cracking. You won't get stress corrosion cracking if you're cathodically protected, but you might introduce hydrogen and get cracking from that. There's a little heat treating shop over here near the airport once, a number of years ago, and they had just put in a big steel tank where they were going to heat treat they were making steel toes. I was surprised they were doing this in the United States, but the steel toes for steel toe boots, okay? And they're very high strength steel, very ductile steel, because you want lightweight steel toes and you don't want them to crack if you drop a brick on them or whatever. And so they were putting in a big heat treating tank, and it was all welded construction, and they were filling it up like a swimming pool, about 50 yards long and about 5 yards wide and 3 yards deep. And all of a sudden it started leaking. There were cracks. And it turns out, I looked at the cracks around the welds, weld residual stresses, clearly looked like stress corrosion cracking. And I go to look in the literature and I find that they were using sodium nitrate salts for the heat treating bath. And I found that, oh yeah, this is steel and sodium nitrate is susceptible to stress corrosion cracking. So the guys I was working with, this firm that Steve used to work with, the guy wanted to run a test. So we did a test. We just made a U-bend out of some of the pieces of steel, put a bolt through it, stuck it in the solution, and made it anodic. Couldn't crack it. We ran tests for 3 weeks and we couldn't crack it. And finally I thought, you know, the literature says it's stress corrosion cracking. What if it's actually hydrogen embrittlement? And so I switched the polarity on the test, broke within 24 hours, okay? So polarity does make a difference. And it turns out the literature was wrong. They called it stress corrosion cracking. It was actually hydrogen embrittlement. But most of the time, metallurgists don't even make a distinction, okay? But there can be a distinction. In that case, it was a big distinction. And all of a sudden, we had the right mechanism and everybody was happy, okay? So hydrogen embrittlement occurs all the time. The U.S. Navy down here in Groton was going to a higher strength submarine steel from HY80 to HY100. Didn't seem like a big change. They had promised Congress, this was early 90s, that they would eventually start making the 21st century submarine out of HY130, which they had developed in the 1960s, but they had never had the nerve to actually build a whole ship out of. So they're starting to build a whole ship out of whole ship? Yeah, a whole ship. The Seawolf, the first edition of the 21st century submarine, is around 1992. And so it's higher strength by 20 KSI, going from 80 to 100 KSI yield strength for this high strength steel. And a grinder, they look for flaws that are 1/8 of an inch in size or larger, and without going through fracture mechanics. All their inspectors had looked for those, found none in the welds. And some guys grinding the surface of the hull to make a smooth contour. You can't even have a little weld reinforcement when you're going through the water. It creates enough noise that they can pick it up on sonar, okay? So they have to grind it smooth. And this grinder's grinding, and he noticed that the grinding swarf, the little iron oxide particles, was sort of lining up in these little less than 1/8 of an inch long parts in the weld metal. And he was smart enough to tell someone. And they came in, they did more thorough non-destructive testing, and all the welds, 18% of the hull had been completed. All the welds were full of little microscopic cracks, okay? They had never seen before. And so it ended up, they had to scrap the whole 18% of the vessel. It slowed down the whole program by about a year. It ended up costing the Navy about $2 billion, okay, to fix the problem. And one of the ways you fix the problem is you heat the steel, okay? You have to preheat the steel so that when you're heating it, it's like it's already in an oven. You know, the heat from welding raises the temperature above that 375, and it'll diffuse out after you finish making your weld. It's still hot, and the hydrogen diffuses out. Well, the harder the steel is to weld, the higher the temperature you have to preheat. And so for this particular steel, which is highly alloyed, they actually had people going in and welding in what they called blue jelly suits, because they had to preheat the steel to 400 degrees Fahrenheit. And these guys were literally welding inside an oven. They had a mask, so they didn't have to breathe 400-degree air, okay? And they would wear a suit it was a blue liquid, and they actually recirculated the liquid. And I mean, these guys were sent into these closed containers in the ship to weld the steel together and it was heated to 400 degrees Fahrenheit. That's how desperate they were to keep welding, so Congress wouldn't cancel the whole multi-billion-dollar program. Anyway, there are lots of different types of steels. If you go looking at the metallurgy of steel, again, how many people in here are not course 3 grads? Okay, so half of you. I'm going to show you a phase diagram. I apologize. Not everybody can appreciate phase diagrams. However, this phase diagram, you should learn to appreciate, those of you in course 3. This is the iron carbon phase diagram. Has anyone who's in course 3 not ever seen this before? Okay, so you've all seen it. I had a graduate student once who had been in mechanical engineering from another university, and Professor Elliott, who's passed away, put up the iron carbon phase diagram in a class and just started talking about it. And the student raised his hand and says, "Professor, can you explain what that is?" He says, "You've never seen this iron carbon phase diagram?" Just try to humiliate him in front of the class. Anyway, this is the iron carbon phase diagram. Steels are everything on this side below about 1% carbon. The maker of this diagram, it doesn't say it on this one, is a guy named John Chipman. Okay, our departmental, breakout room is the Chipman room. John Chipman taught the world how to make steel about 1940. Okay, and he's in the steel industry. He's a hero. And anyway, we'll talk about Chipman some other time. In any case, this is the iron carbon phase diagram. Steel has a face-centered cubic crystal structure up here, body-centered cubic, and you can go through, you can quench it, you can heat it up in this region, quench it down to this region, and it will form a metastable body-centered tetragonal, similar to body-centered cubic, which is martensite, which is extremely hard. You can go from this 30 KSI type material that you started with, you formed into a sword or bolt or whatever, when it was soft, and you can quench it in water or oil. The swords, they used to take a living slave. They thought this gave the swords more power if you took a slave and you just quenched it by sticking a hot sword right through them. Well, lose more slaves that way. But anyway, but it's true. They thought this gave it the steel vitality. Okay, this is sort of making someone sick in the back. Anyway, but this is the way it was. I mean, the world was different. Actually, the world is still the same thing, same way in certain parts of the world. But anyway, it's okay. It cauterizes the wound, the hot steel. Anyway, hey, we used to do it in this country. I don't know if I told you that my oldest daughter was born in St. Elizabeth's Hospital in Bethlehem, Pennsylvania. Beautiful hospital, because they were always bringing maimed steel workers down to the hospital. I mean, some guy get his arm cut off by a piece of hot steel. Just slice through your arm like butter, but there's no bleeding because it cauterizes it as it goes. Anyway, so you quench it and you get an increase of 5 or 10 in strength. Okay? Except now it's so strong that it's somewhat brittle and you have to temper the steel. So you go to True Value hardware store and you'll see True Temper tools. They've heated it, they've quenched it in water or oil. They then have to temper it to 500 or 1,000 degrees Fahrenheit. This is on this 1,000 degrees Fahrenheit's right in here. You tend to avoid the 600 to 900 range because the steel can get brittle for other reasons. And this explains one of the reasons why there are so many steels. Okay, there are so many steels because there's several things. One's called hardness, one's called hardenability, and then the other is called hardening ability. So this is out of a materials dictionary. And if you look at hardness, hardness is the resistance of any material to indentation. So a hardness test, you take either a diamond or a hard steel ball and you just put a weight on it and you see how deep it goes into the surface of the material. You're probably only going to go in 100 microns deep, a little thicker than a human hair, to get a little indent, and you measure the depth very precisely in a special machine and you get a hardness number. And so this is used all the time in industry. If you go out and get a bunch of them done at some testing lab, they'll charge you $5 a pop, okay, to get a hardness test done. There's hardenability in ferrous alloys, meaning steel, the property associated with chemical composition of the base metal, which determines the depth and distribution of hardness that can be induced by quenching. And well, I told you about quenching, and how deep will that go, and how is it distributed? The hardness will be maximum at the surface and it will die off, but how does it die off? And there are whole books listing all the different steels, showing you the depth of stuff. And so 100 years ago, if you had been a graduate student in this department, you might have been generating these plots for different compositions of steels and trying to understand why different things do different things. Different steel compositions behave the way they do. Hardening ability is, in steels, the property that describes the maximum hardness a base metal can be treated. It turns out the maximum hardness is very strongly a function of the carbon content of this iron carbon alloy. If you're over here at 0.1% carbon, like automotive steels, the maximum hardness might be Rockwell C25. Whereas if you're over here at 0.6% carbon, only 6 times as much, the maximum hardenability might be Rockwell C60. Well, Rockwell C60 is as hard as a file, okay? And if I put it in a vise like this and hit it with a hammer, it probably, even after it's been tempered, I could probably shatter the file if I hit it hard enough. Take that 1010 steel they might make an automotive sheet out of, quench it and temper it. I can't get 200 KSI strength like a nail file or a metal file, but if I put it in there and I quench it in water and I do it well enough, I might be able to get 100 KSI. Okay? I can't get 200 KSI. So the carbon content's important. So if I start looking at the actual compositions of steels, these are transformation curves, we don't have to go through that. Actually, this is the plot of hardness versus carbon content. And you can see at low carbon contents, you're going to be Rockwell C25, and higher carbon contents, you'll get up. Actually, this one is, this is hardness of pearlite at the nose of the curve. This is not the one I'm thinking of. This one would be 0.1, but it's a similar shaped curve. The increasing in carbon and then leveling off. That's not the one I really wanted. But there are lots of steels. Let me just finish this up briefly. And we'll talk some more on Monday. But they have different designations. A 1050 steel has 0.5 carbon, a 1065 has 0.65 carbon. And then, so these are all the plain carbon steels, and then you get down here to the ones that are 4,000 or 5,000, and those are what we call alloy steels. They have nickel, chrome, vanadium, niobium alloying elements, and they will have different amounts of carbon, but they have different alloying elements. Some of these things, the plain carbon steels, you probably can't harden more than 1/8 of an inch deep. But if you start putting nickel and chrome and things, you can make something 4 inches thick or 8 inches thick that has a hardening depth, a hardening ability, or a hardenability that can go for 8 inches deep. Okay? If you don't put the alloying elements in, you'll get just the top 1/8 of an inch that's hardened. Okay, so you need to add alloying elements for heavy steels. You need to adjust the carbon for the maximum hardness you're going to get. And if you're an automotive company, you want just the right amount of everything, because it can make a difference of $10 a ton or $20 a ton. And if you're buying 1 million tons, then it makes a difference. Okay? And so there are literally hundreds of steel compositions. And you need to be a heat treater a steel heat treater to be able to figure out which one of these you're going to use. Okay, but it's because mostly the automotive industry and railroad industries, they want just the right composition for their thickness and their wear resistance or corrosion resistance or whatever. And so they use different alloying elements, different amounts of carbon, and so there are literally hundreds of variations, because when people buy 1 million tons of steel, they want the lowest possible price, and tenths of a penny per pound make a big difference. Okay, so I'll see you Monday. I'm actually lecturing